I'm John Levy, the CEO of SEEQC. SEEQC stands for Scalable Energy Efficient Quantum Computing. And first off, I want to thank Mark, thank Crystal and Celia and the QED-C team for inviting me here today, and great that Matt's joining us as well as the other participants today. If we were having this discussion, a presentation around quantum computing, I don't know, 7, maybe 5 years ago even, we might ask the question around, can we build a quantum computer? Can it run an algorithm? Can it do anything you can't do on a classical computer? I think all of those questions have basically been answered, maybe the last one, some controversy. But where we haven't really figured out is, as an industry, is really to think about scaling, and scaling in a significant way. And so that is our sole purpose, is to function around a scaling model, and I'll see if I can make the case for what we're doing. So we're a company that spun out of a company called Hypris. Many of you may know us. We're the world leader in digital superconductive electronics, with its roots in IBM going back decades. Our systems are based entirely on single flux quantum. So we find CMOS circuitry great for computers and cell phones, etc. But frankly, too slow, require too much energy and heat dissipation, and too much noise. And so our systems operate typically between 30 and 40 gigahertz. We've built classical logic operating at 750 gigahertz, the fastest digital logic in the world. We operate at 3 to 5 orders of magnitude lower power, and we operate at a nearly zero noise floor. We do that in a chip foundry, not unlike Rigetti, although our chip foundry is for more classical electronics, but again, these are all single flux quantum as opposed to CMOS, so we see those advantages. And we have customers. We built some of IBM's first qubits back in 2003. We were building circuits for D-Wave. We built circuits for the DOE, DoD, NASA, etc. So we have lots of customers, commercial, government, and academic. So what's the theory of what we're doing? Well, if we go back to the early days of classical computing, we're seeing examples like this. This is a digital computer, the ENIAC computer, but it was never built to scale. It was, just so you know, it was highly error prone, lots of complexity, lots of cost, and it was built around vacuum tubes, which were obviously not going to scale. And it took, the invention of the transistor a year later at Bell Labs, the integrated circuit at Fairchild, the microprocessor at Intel, before you could actually get to something that was kind of enterprise grade. And this is the kind of thing that we're seeing at the IBM 360 as an example. So if we think about where we are in the quantum industry, we sort of think metaphorically, we're back in 1946. And the image on the right is a typical superconductive electronic quantum computer, the likes of which you might see at Google or IBM or Rigetti or others. And what we think is that we need to go through this process of integration to build the world's first all chip-based quantum computer. And to do that, what we've effectively done is replaced all the racks of equipment, all the connectivity, operating at going from low temperature superconductive temperature to room temperature, back to superconductive temperature, going from analog to digital to analog, all that complexity, cost, etc. And we've reduced it to a series of chips that look just like this. So this is a single flux quantum chip. This is in a reconfigurable architecture. This is an example of an entire control chip for a quantum computer. So imagine for a moment, if we go back to what this looks like and all the electronics that are needed to do that, and imagine you can put this in a multi-chip module where we have 5 picosecond latency between readout control and the quantum layer, and that you can do this in a way where we can operate at 20 millikelvin with control readout and control electronics. And then this is what an entirely chip-based architecture looks like. This is based on a computer that we're building on an application-specific basis for Merck. We've recently announced a partnership with BASF. And we have other commercial partnerships as well. But this is, to be clear, an entirely chip-based system going from the quantum layer all the way up to readout control, quantum error correction, SFQ controller, classical memory, so we don't have to go out to the web for classical resources, and even a nod to cryo-CMOS for memory. And this is a computer that we're building now, and is going to be going online probably within the next 2 to 3 years. Again, manufactured in our chip foundry in Elmsford, New York. We have facilities as well in London and in Italy. And our business model is very similar to what NVIDIA is doing on their cloud business, where essentially they began by building application-specific chipsets, which then migrated into their cloud system. So we're happy to talk to you more about what we're doing. We're actively working on corporate partnerships. We're, of course, always looking at investment, so we're happy to do that, and also working with quantum software developers. We're working with groups like QCware, Riverlane, and others, and happy to expand that for our platform. And with that, I thank you very much.